Hello and welcome. Hi, my name is Lucinda Offer. I'm the Education Outreach Officer for the Royal Astronomical Society. And welcome to the RAS Public Talk for March 2024. I am so happy to welcome our speaker today, Dr. Marie van de Sande, who is our 2023 Caroline Herschel Prize Lectureship winner, which was established in 2018 by what is now the Herschel Society in association with the Royal Astronomical Society to celebrate Caroline's memory by supporting promising women astronomers early in their careers. And she is also an Oort Fellow at Leiden Observatory at Leiden University in the Netherlands, and she studies the chemistry around dying sun-like stars by developing novel chemical models and comparing their results to observations. Mary obtained her PhD in 2018 from KU Leuven in Belgium, where she stayed on as a fellow of the Research Foundation Flanders. She moved to the University of Leeds as a Mary Sklodowska-Curie individual fellow in 2021 and relocated to Leiden in September of 2023. Please welcome our speaker, Dr. Marie van de Sande.
Right. Thank you for the kind introduction. And can you hear me okay? Are the microphones? Okay, wonderful. Well, so thank you again for the very kind introduction. It's an honor to be here at the Royal Astronomical Society, especially since I published a few papers with the monthly notices of the Royal Astronomical Society. So this is quite special. Let me just try to change slides. All right, that's working. Wonderful. But it's especially a great privilege to be here to talk about the exciting research field of astrochemistry and how it's linked to Caroline Herschel's research. So since it's quite a long talk, I have divided it into 3 sections. So I'll begin with just general astrochemistry. I'll then talk about the astrochemistry of dying stars, which is my field of research. And then I'll finish with how we go from dust produced by these dying stars to us, to life here on Earth. Now, when you think about astronomy, you maybe think about very large things. There's very large stars out there that make our sun seem like just a tiny marble. Or maybe you're thinking of very extreme things, such as neutron stars, which are the size of the Earth, but contain twice the mass of the sun. Maybe you're thinking about even larger scale stuff, galaxies and clusters of galaxies, far beyond the Milky Way on length scales that are much beyond our, well, my comprehension at least. But if we want to understand the workings of our galaxy and really understand where we come from, we have to take a look at smaller things. And by small, I mean very small. You have to take a look at atoms and molecules. So let's have a bit of a history lesson. During the Big Bang, only hydrogen, helium, and a little bit of lithium was formed. Everything else, the carbon in our bodies, the oxygen in the air, all the heavy metals in these computers and projectors, were all forged in the hot cores of stars that died a long time ago. And somehow we ended up with this configuration, our Earth with us on it. And to understand exactly how how stars and planets are being formed and where we come from, we need to take a look at the chemistry that happens along the way. And that's exactly what astrochemistry is about. So astrochemistry is a study of molecules, but not just which molecules are where. It's also about their formation and destruction reactions. So which chemical reactions form or produce a molecule, which chemical reactions destroy a molecule. And we do this in order to see how they influence the structure, evolution, and dynamics of their environment. So that's a very broad definition, but that's also because it covers a very broad range of topics and a very broad range of environments. Throughout the life cycle of a galaxy, you can identify several astrochemical laboratories. So this is a cartoon depicting the life cycle of a galaxy. So stars are formed from clouds of material that occupy the space in between the stars, also called the interstellar medium or the ISM. And then the life and death of a star all depends on its initial mass or its birth weight. Stars which have an initial mass of at least 8 times that of our sun will explode quite dramatically at the end of their lives in a supernova explosion, throwing all of their outer layers back into the ISM, so all of the heavy elements produced in their cores back into the ISM. The only thing that will be left behind is either a neutron star or a black hole, again, depending on its initial mass. Stars like our sun don't die in such a violent way. They do die, but just rather than throwing everything out all in one go in an explosion, they lose their outer layers by means of a gentle stellar outflow. The only thing that will be left behind is a white dwarf. So as stars die, they eject, well, yeah, they sort of contribute their life's work, their ashes back into the ISM, enriching it with new heavy chemical elements. So it's sort of like a cumulative reincarnation. You're born from the ISM, and as you died, you contribute back into the ISM. And astrochemistry helps us understand exactly how, well, the different stages of the life cycle of a galaxy. So astrochemistry is quite a young research field. The first molecules were detected in the 1940s. So these are CN, so the cyanide radical, CH, and CH minus, so CH with an extra electron added onto it. And they were detected in the tenuous environment of the interstellar medium. And the detection came as quite a surprise because, well, a surprise both to astronomers and to chemists, because you wouldn't expect molecules to be there, since the ISM, and space in general, is quite a hostile and unfriendly environment for molecules. It's hostile for two main reasons. You've got density and you've got UV radiation, so ultraviolet radiation. Let's start with the first issue, density. So these molecules were detected in very tenuous regions of the interstellar medium, where the densities are 10 to 100 particles per cubic centimeter. And that's not a lot at all, especially when you compare it to this room, where we have about 10 to the power 19 particles per cubic centimeter. So 10 to 100, that's not a perfect vacuum, but we're getting quite close there. But so if you want to form a molecule, you need two atoms bumping into each other and then forming a molecular bond. But at such low densities, it can take quite some time before you meet somebody else to form a molecule with. In fact, it can take centuries before you're able to form a molecule. So that's a long time to wait. But these these atoms spend around like a few thousand, maybe 10,000 years in such diffuse clouds. So even though it takes a very long time, time is on your side and you will find another atom eventually to form a molecule with. But then we have the other issue, namely ultraviolet radiation. And I think I can say that we've all experienced the nefarious effects of UV radiation here on Earth, namely a sunburn. And every summer I still get a sunburn, even though the sun doesn't emit that much of its energy in the UV. And also we're protected by a very thick atmosphere that filters out most of the UV rays. Still, every year I get a sunburn. If you're a molecule in the ISM, you are not protected by a thick atmosphere. And what's more, you're surrounded by a bunch of different stars, also very massive stars, who just blast UV radiation in your general direction. And the molecular equivalent of getting a sunburn is to be photodissociated. So a UV photon hits a molecule, breaks it apart, and you're back into your atomic state. So you've waited for centuries to finally form a molecule, and then all it takes is one photon to break you apart and become an atom again. But despite these hostile conditions, we still find molecules. And many more molecules have been detected. The field really started booming in the 1960s when radar equipment left over from the Second World War was pointed towards the sky. So rather than like tracking your enemy, you can just use it as a radio telescope. And this led to an increase in the number of molecules detected. So that's what's shown in this graph. In the 1940s, we have a few, but then as radio astronomy comes online, you see that the number of molecules really goes up, and the slope, so the amount with which we detect them per year, really increases as technology increases as well. So the main astrochemical observatories now are ALMA, so the Atacama Large Submillimeter Array, which is an array of 66 radio telescopes in the Atacama Desert in Chile. So 66 telescopes collaborating and working together as one enormous one. And then, of course, you have the newly launched James Webb Space Telescope, which is also opening up a whole new field. Right, this is a census of the molecules detected so far divided by the number of atoms. So up to date, so roughly 300 different types of molecules have been detected. Most of them are quite simple, containing 2 to 3 atoms. But as well, technology continues to develop, and also as we continue to observe, this higher end is starting to be filled up. So most are very simple. The most abundant molecule is H2, the hydrogen molecule, simply because, well, almost 3/4 of everything is hydrogen. You also have CO, carbon monoxide, water, HCN, lots of molecules we know floating around in space. But there's also some quite strange molecules, for example, HC3N, which is a linear molecule. So you've got 3 carbon atoms in a row, topped off by a nitrogen on one end and a hydrogen on the other end. So if HC3N were to walk into this room, it would be hydrogenated in no time because, well, the density is quite high, there's lots of water, and this molecule has lots of unpaired electrons ready to react. But in space, the conditions are just right for HC3N to exist quite abundantly. You can make it on Earth, but it's an expensive process. And completely on the far side here, the longest molecule detected so far is C60, or Buckminster fullerene. And C60 takes the form of spherical, it's just a ball, it's a buckyball. So 60 carbon atoms all arranged into a spherical shape. You might wonder why we go through all these efforts to detect molecules, and it's because they are very sensitive probes to the physics. For something like HC3N to exist, we know that the density should be quite high because, well, there's 4 atoms involved in one molecule, so they had to meet each other in a timely manner. And also, the UV radiation field shouldn't be too large because otherwise it would have been broken up and it wouldn't have been able to get so long. So chemistry is really a way to pin down the physics in more detail. And chemistry can then help you unravel just the structure, the dynamics, and the evolutionary state of your environment in which they're found. So chemistry aiding physics in a way. Right, so let's now start a journey along the life cycle of a galaxy and following the chemistry along the way. And why not start at the end with the astrochemistry of dying stars? So here we are again at our life cycle of a galaxy, and massive stars, towards the end of their lives, when they run out of hydrogen in their cores, they will swell up and become a red supergiant. So about, well, several hundred times the radius of the sun. A famous example is Betelgeuse in the constellation of Orion. Betelgeuse is this really bright red guy over there. I'm not sure about the center of London, but in any other town, you could see Betelgeuse quite easily with a naked eye, but maybe not here. I haven't tried yet. So Betelgeuse is about 700 times the size of the sun and will explode as a supernova relatively soon in the next few hundreds of years, because that's the end of these stars. After a while, they can't support their own gravity anymore and they collapse onto themselves. And as a result, they also explode as a supernova, throwing everything out all in one go. A famous example of a supernova is SN 9087A. It's the first supernova to go off in 1987. And it's quite a famous one because it's also the first supernova that we were able to track with modern astronomical techniques. So there's lots of papers and conferences just about this object. At the center, well, so the remnant of the supernova is a neutron star. Another nice example of a supernova remnant is the Crab Nebula. That's whatever is left over from a supernova that went off in 1054, which was documented by Chinese astronomers. And then its core lies, well, the remnant is also a neutron star, but a highly magnetized neutron star that's rotating. So that's a pulsar. If you're even more massive than these stars were when they were still alive, you might become a black hole. So that's all very imaginative. It really speaks to the imagination. A supernova explosion, drama, wonderful. But most stars don't die that way. Most stars are stars like our sun, and they die a much more quiet, gentle death, not very dramatic at all. So as the sun will run out of hydrogen in its core, it would also swell up, but become a red giant rather than a supergiant, so a few 10 times its size rather than a few 100 times its size. And then afterwards, it will also lose its outer layers back into the interstellar medium, but rather than all in one go, it will do so via a very gentle, steady outflow, a wind of material blowing into the interstellar medium. The thing that will be left behind is a white dwarf, and for a very brief period of time, the white dwarf is able to light up the material that has just been lost and form a planetary nebula. So the outflow part happens during the asymptotic giant branch phase, or the AGB phase. And it's a very descriptive name if you're an astronomer, but admittedly, it's not the best for PR purposes. Supernova does have a better ring to it, of course. But this is an AGB star in all its glory. It's an image taken by the Hubble Space Telescope of IRC 10^16, also known as CW Leo. So here you see this outflow of material moving away from the star into the interstellar medium. And this is quite a large object, so it spans about 2,000 astronomical units, where an astronomical unit is the average distance between the sun and the Earth. So that's very large, especially when you keep in mind that our solar system is only like a few hundred AU. So that's a very large object, spreading just a very large object, very large outflow moving into the interstellar medium. In fact, you can't see IRC 10^16 itself because it's hidden by all the material that it's expelling. More specifically, it's hidden by all the dust that's being formed in the outflow. And that's really something quite special because we have here a phase transition from the gas phase to the solid state. That's very difficult to achieve in space. And the outflows of these AGB stars are one of the few places where you can efficiently form a lot of dust. These dying solar-like stars are very efficient dust factories, and that makes them really quite special. And through their outflow, they will contribute all of the heavy elements that they forged in their cores back into the interstellar medium, but also lots of this dust that they just formed. And this is another image of an AGB star, now taken in the UV, of Myra. Myra is somewhere here on the right. It's losing its outflow, blowing a bubble, but it's also moving through space. And then as it does so, it loses material and leaves behind this tail of gas and dust. And the tail in total is some 13 light years long. So here you see an AGB star efficiently polluting its environment. So let's now dive into the chemistry of these outflows because they're very rich environments hosting different types of chemistry, including dust formation. So here in this cartoon, I show you half of an AGB star at the left. And the type of chemistry of the outflow is determined by the elemental carbon to oxygen ratio of the star itself. And that's because carbon and oxygen, if you put them together, they really want to form carbon monoxide, CO. So if you have a C/O ratio smaller than 1, that means you have more oxygen than carbon. You can then assume that most of your carbon will be locked up into CO, leaving behind only oxygen, so you'll have an oxygen-rich outflow. Now, during the AGB phase, there is a process that occurs. It's called a dredge-up. That's, again, a very descriptive way because it dredges material from the core, so newly formed carbon, up to the stellar surface. And with each dredge-up, your C/O ratio increases and your star steadily becomes a bit more carbon-rich. And after a while, well, C/O ratio will be larger than 1, so you will have more carbon and oxygen, so we will now have a carbon-rich chemistry. Now, our sun will never become a carbon-rich star because it's not massive enough. It will not experience enough dredge-ups during its lifetime on the AGB. So the chemistry of your AGB star really depends both on the age of your star, but also on its initial mass. Not all stars will become carbon-rich. Right, the star itself isn't very well behaving. The outer layers are very convective. And these This is a simulation of an AGB star. So you see these huge convective bubbles moving away from the star, pushing material away, and then it's falling back. It's like an enormous pot of boiling water. And these movements of material cause shocks that take the chemistry out of equilibrium. So very close to the sun, well, yeah, after 4 billion years, yeah, but very close to the star, we have a non-equilibrium chemistry precisely because of these huge convective motions. Then a bit further out, the density is still high enough, but the temperature is low enough for dust to condense from the gas phase. And this is really quite special, as I mentioned before, because we have the phase transition from gas phase to the solid state. And the type of dust that you form depends on the chemistry of your outflow. So if you have an oxygen-rich star, you will create metal oxides and silicates, so lots of tiny sand grains. If you have a carbon-rich star, you will be creating amorphous carbon mostly, which is just basically soot. These carbon-rich AGB stars are very, enormous combustion engines in a way. Now, this dust is opaque to the infrared radiation of your star. That means when an infrared photon hits the dust grain, it transfers its momentum onto the dust, so the dust starts to accelerate away from the star, and as it moves away from the star, it bumps into the gas, drags it along, and launches the outflow. So it's a process, the chemical process of dust formation that launches your outflow and it determines the subsequent evolution of your star. So it's sort of chemistry that kills off your solar-like star. And then finally, in the outer regions, the material has reached its terminal velocity, which ranges between 5 to maybe 30 kilometers per second, which isn't very fast at all in astronomical terms. And the chemistry in this region is a very rich photochemistry, since photons from the interstellar radiation field, so that's just the sum of all the stars around you, are able to reach this region and create a very reactive soup of atoms, molecules, and ions. So within one environment, we've got 3 different types of chemistry, including dust formation. And this richness in different types of chemistry is because we are dealing with an outflow, which means we've got these large gradients in density and temperature. In the inner wind, we've got densities of about like 10 to the 13 particles per cubic centimeter, temperatures of a few thousand Kelvin. And as we move away from the star, when the outflow merges with the ISM, we've got densities of like 10 particles per cubic centimeter and temperatures of some 10 Kelvin as well. So these are huge gradients that give rise to different types of chemistry. Now, you would think that maybe like a spherically symmetric star would give rise to a spherically symmetric outflow, but of course, nothing is quite as easy as it seems. And lots of intricate structures have been detected. So this is a spiral as observed by ALMA. So this is emission of carbon monoxide around our sculptoris. And you see that there's a spiral within the outflow. Another famous example is L2 Puppis. So this is an observation in the optical taken by the Very Large Telescope in Chile. This dark band is caused by a dusty disk that hides whatever's going on from our view. And these 2 cones of light is light that's being scattered off the dusty disk. If you combine that with ALMA observations, you find that there's a tentative detection of a planet a bit more massive than Jupiter. And if we were to bring it back to our solar system, it would be roughly at the orbit of Uranus. And you can maybe look at this image as sort of a glimpse into our future, because L2 Puppis used to be very similar to our sun, the same initial mass of 1 solar mass. And well, we also have a massive planet towards the outskirts of our solar system, namely Jupiter. So this is maybe what's in store for us in a few billion years. But as observations continue to go on, more and more of these structures are detected, and it seems that spherically symmetric outflows are the exception rather than the rule. So these are 12 oxygen-rich outflows, again, all in CO. The red is moving away from you, the blue is coming towards us, the green is in the plane of the sky. None of these outflows are spherically symmetric. Some a bit more so than others. So these guys just have a few spiral arms. That's fine. We've got a bipolar structure over here. And this is some sort of a space rose. And this star, Pi 1 Rho, has both a disk and a spiral, so it's really a mess. And we think that these large-scale structures are caused by binary interaction. So almost all stars have a stellar companion, one or more stellar companions, so they're all orbiting around each other. If you don't have a stellar companion like our sun, you probably have a massive planetary companion like Jupiter. And these massive, these stellar companions or your planetary companions are massive enough to sort of grab the outflow and shape it into such an intricate structure like a spiral or a disk or something in between. And this links the AGB phase to the next stage in stellar evolution, which is the planetary nebula phase. And it has long been known that planetary nebulae have come in a very wide range of shapes. Some are well-behaved and quite spherically symmetric, and others are called the red rectangle because they're the red rectangle. And it's long been an issue of how do you go from a spherically symmetric star to something like the red rectangle. So maybe this shaping mechanism is already starting in the AGB phase, where it's being carved out by a binary interaction. So either with a fellow star or one of your massive planets. And the planetary nebulae are actually linked to William Herschel. So Caroline was tasked to go look for nebulae, as in clouds of material within the interstellar medium. And she showed that you can detect quite a few nebulae if you use just a basic telescope, which showed to her brother William that if you use his fancy telescope, you can detect many more, and that sort of inspired him to go build his very famous catalogue of nebulae. But while he was looking for all these clouds of material, he also encountered some weird things, such as the Saturn Nebula. And he described this nebula as a curious nebula, or what else to call it, I do not know. These objects seem to be planets of the starry kind. He, of course, didn't know that he was looking at a death throes of a star rather than, well, a planet of the starry kinds. He called it a planetary nebula, and even though it's a wrong name, it stuck around and we still call it a planetary nebula. All right, so finally, our star is dead. The end of the star has died, but the life cycle of our dust has only just begun, because as it died, it expelled all this dust into the interstellar medium, where it plays a very important role to the physics and chemistry of that medium, but also to star and planet formation. So even though we don't know exactly how dust is being formed, we do know that it plays an important role. So let's hop onto the dust and see where it takes us. So I said before that most of the ISM is very tenuous and opaque. Very tenuous, so not a lot at all. It's not a complete vacuum, but I mean, it's getting close there. But you also have regions of higher density. So this is a dark cloud where the density is about 10,000 to 1,000,000 particles per cubic centimeter. So that's much more than 10, but still not a lot at all compared to this room. And I think it's quite clear why it's called a dark cloud. It looks like there's a hole in the sky, which is maybe a bit concerning. But this is just a dense cloud of material, and it will collapse under its own weight sometime in the next thousands of years and become a stellar nursery. But because there's a higher density, it means there's also more dust grains. And if we were now to switch wavelengths, we can peek behind the dust grains and see in the infrared, yeah, of course, great, there's no hole in the sky, there's plenty of stars behind it. And this really showcases one of the properties of dust, which is to shield against ultraviolet and visible light. And that's very important for chemistry, because the dust sort of acts like a sunblock for all the chemistry that happens inside of this dark cloud. So protects it against all the UV radiation that's out there to photodissociate all of your molecules. So because of that property, we can distinguish different types of chemistry throughout the ISM. So in the more tenuous regions, we have very simple chemistry. So it's mostly atoms and ions, some simple molecules such as H2, CO, CN, CH, for example. Then as we increase the density, we've got a bit more longer guys showing up, ones we know, such as water and hydrogen cyanide. You also have formaldehyde floating around, but then of course, some quite exotic molecules such as C4H. So that's 4 carbon atoms in a row with one hydrogen atom at the end. That's again very difficult to make on Earth, and probably also quite poisonous as well. You wouldn't want to encounter it anyway. But if we go to even higher densities, we find some actually complex molecules floating around, some organic molecules that we remember from our secondary school days, such as formic acid, which is the compound that makes bee stings sting. We also have ethyl formate, which smells like raspberries and tastes of rum. And you also have methanol floating around. So that's the alcohol that will get you drunk, but will also make you blind. That's all floating around in space. And in fact, we see these complex organic molecules at very high densities, at very high abundances, I mean. So the amount with which we observe them is too large to be explained by gas phase chemistry only. So things floating around and bumping into other things. In order to explain the abundances with which we see them, we have to again turn to our friends, the dust grains, because the dust can act as a meeting place for molecules to meet each other and react. So that's shown in this video where you, oh no, my video, oh. I don't know. It should have. Oh, no. Anyway, I will do a dramatic reenactment of the video. It won't be as... Oh, there it is. Oh my God, yeah. Oh my, that's much better than the dramatic reenactment. Let me tell you. Okay, back from the beginning. Okay, please. One more click. Oh, it's taking some time to load. Ah, okay. But that's the end of the... Oh, okay, no, there we go. There we go. Woo! Oh my God, because see, that would have been a pain for me to dramatically reenact. But here we have CO molecules attached to the dust. Well, they're just sitting on the dust. They're forming an ice. The white guys are hydrogen atoms. They don't weigh a lot, so they can zoom around on the surface quite efficiently. And while I was speaking, methanol was formed on the surface. A CO molecule arrived from the gas phase, and beep, HCO is being formed. The hydrogen atoms are zooming around and bumping into them, hydrogenating it. And there we go. Even though they weigh much more, they can still move around, just much more slowly. Another CO atom arrives from the gas phase. These two HCOs are now scanning the surface and finding each other. And we need a few more hydrogens. One more. Just one more, and now we have glycolaldehyde, if I remember correctly. Another CO atom arrives from the gas phase, and it bumps into a hydrogen. And now we have a UV photon striking our methanol, dissociating a hydrogen off, and now they move together and meet the two radicals, forming another complex organic molecule. So this takes some time, but again, we're on this dust grain for quite some time, and your dust grain becomes coated with like an ice mantle of these molecules. And as your dust grain is incorporated in a star-forming region, it heats up, and this evaporates these complex organic molecules off of the dust grain into the gas phase. And that's why we see them at such large abundances. They were formed on the dust grain and then evaporated off as the dust heated off. So dust both protects against UV radiation, and it allows for more complex organic molecules to form, since it provides sort of a catalytic meeting surface. So as your dark cloud starts to collapse, can't withstand its weight anymore, maybe a supernova went off somewhere in the background and gave it a final push, stars are being formed within the cloud, and this is an artist's impression of such a protostar, so baby star, over there, surrounded by a disk of material which is still accreting onto the star. And this disk of material is called a protoplanetary disk, which means that, well, and we call it a protoplanetary disk because this is where planets are formed. And we now know that planet formation is sort of a natural byproduct of star formation. And even, well, we don't know the exact details of planet formation, but we do know that it all starts with dust grains, because you need a few dust grains to stick together and form a larger dust grain, and then you've got a little pebble, and then you've got a rock, and before you know it, you've got a planet. But the before you know it part is quite vague, but it all starts with dust grains. Now, these days, observations are as beautiful, or maybe even more beautiful than artists' impressions. So this is a gallery of protoplanetary disks as observed by ALMA. So what you see here is emission of the dust. They appear to have different shapes, but that's because they have different orientations towards us. But you do see that some of them are quite smooth and others have these dark rings within them. And we think that these gaps are being carved out by planets that are being formed within these disks. So what you see here is sort of a 20-week scan of a planetary system. It's a planetary system in the making. You can also take a look at the different molecules within these disks. So here again, we have the dust at the top, and at the bottom, you've got the emission of different molecules in different colors. And by figuring out which molecules are where, we can figure out more the temperature and the density within the disk, but we can pinpoint exactly how planets are being formed. What you can also do is try to predict what type of planets will be formed within these disks. Are they going to be gas giants like Jupiter, maybe more rocky planets like our Earth? That's all encrypted within the chemistry of your protoplanetary disk. Yeah. Now, at the end, you end up with a planetary system, and a planetary system we know the best is our solar system, and this is a very zoomed out view of the solar system. So on the left, we have the sun. On the right, we've got our closest stellar neighbor, namely Alpha Centauri. We've got all of the planets over here, but there's also a bunch of leftover material from when we were in a disk. So you have the asteroid belt between Mars and Jupiter. You've got the Kuiper belt, which is behind all of the planets, and then everything surrounding it all, we have the Oort cloud. And these are all remnants from the disk from which we are formed. And sometimes they fall onto the Earth, and most of the time such an asteroid impact is not a big deal, but sometimes all the dinosaurs die, so it really is a little bit of hit and miss. But we also have more benevolent visitors, namely comets. They originate from the Kuiper belt and the Oort cloud, and they're thought to be very pristine remnants from the disk from which we are formed. So studying them means that you are studying, so it's like studying a historical artifact. Now, Caroline Herschel also studied comets, and she detected 8 of them. And after the detection of her 3rd comet, this cartoon was published, and it shows a comet farting in her general direction. And she's looking at it, and the text says, "What a curious sulfuric smell emanates from this meteor." So it was clearly meant to mock her for doing the very unladylike pursuit of being an astronomer. And I'm very happy that whenever I publish something, people don't make cartoons like that, or at least not that I know of. So things have gotten better. But yeah, Caroline discovered 8 comets. And because there's such pristine relics of the disk from which we are formed, it's well worth studying them. And that's why in 2014, the European Space Agency Rosetta mission finally reached its goal of the comet 67 Churyumov-Gerasimenko, or 67P. And this is an image of the core of this comet, so the nucleus. And you might have heard comets described as being dirty snowballs. Well, that's not a ball. That's more 2 things sticking against to each other. So that already tells you something about how we built the environment in which it was formed. And then you also see these like rays emanating from the surface, maybe, yeah. Well, believe me, they're there. And that's material being outgassed from the surface. So this comet's nucleus is coated by ices. And as the comet approaches the sun, it warms up. So you sort of sublimate these ices off back into the gas phase. Now, the Rosetta mission also took this very nice sequence of images where you see the surface of this comet. This is a cliff of about like 20 to 30 meters high. We've got some rocks lying around on the surface. The stripy things you see are mostly cosmic rays hitting the camera, but the fluffy things is more like snow floating around on the comet. So here you have sort of the geology of the comet as well as the weather on it. So the Rosetta mission sniffed out everything that came off the comet and found a real zoo of molecules. So you've got lots of smelly ones containing sulfur, you've got salty ones, you've got all your alcohols, you've got carbon chains, you've got very poisonous ones. But the king of the zoo is glycine. And glycine is the simplest amino acids. And amino acids are proteins that are essential for life on Earth. And this simple amino acids is detected on a comet, where it was formed purely by astrochemical reactions, astrochemical means. And this feeds into one of the theories of life on Earth, because we know that early Earth experienced lots of bombardment, and these asteroids and comets were all coated with ices. And this is where we got most of our water from, so water has an extraterrestrial origin. But maybe these comets didn't just bring, and these asteroids didn't just bring water, maybe they also brought other molecules, like glycine, simple proteins, simple sugars, perhaps simple fats as well, ingredients to really kickstart the origin of life. So perhaps like planet formation is a natural byproduct of star formation, maybe life is sort of a chemical byproduct of planet formation if you're lucky enough, right? So when you think about the formation of stars and galaxies, how you go from a dark cloud to a protostar surrounded by a protoplanetary disk to finally a star and its planetary system, shouldn't forget that it's all starts out with gas and the dust provided by stars that died a long time ago. And because these dying stars see the universe with the building blocks of the next generation. So it's therefore important to understand stars die if we want to know if how stars and planets are being formed. And astrochemistry plays a crucial role, since it's the chemical process of dust formation that really kickstarts the end of life of most stars, stars like our sun. And by studying dust formation, we can understand how these stars die, which is useful for stellar evolution, but also we understand exactly what type of dust is being formed, how big the dust grains are, and we can then follow the chemistry of these dust grains as we go through this entire process. Now, astrochemistry isn't just observations alone. Of course, they play a large role because we need to see which molecules are where, but you also really rely on laboratory experiments. You need a lot of spectroscopy in order to be able to identify the molecules in your observations, but you also need a lot of laboratory work to determine how fast chemical reactions go at the conditions of space, at these low temperatures and low densities. So that's a lot of work in the lab. And then you have a third pillar, which is theoretical models that take the input of these laboratory experiments and try to reproduce your observations. And then by comparing your model to your observations, you can pin down the physics, you can see where you're going right, you can see where you're going wrong. So astrochemistry really depends on all three of these components, and they all need each other. So there's many ways to help answer the question of where do we come from? And I'd like to end my talk with this image, which was taken by the Voyager 1 on Valentine's Day of 1990, right when it was about to leave the solar system. It looked back one more time and took this picture of our Earth. And in case you can't see the Earth, that's the little pixel over there. And this really is a group picture of all of humanity, because everybody who had already died or was alive at the time is in this image. But also everybody who didn't exist yet is there, because all the material needed for our existence is all in this one pixel, brought to us from, well, all formed in the cores of stars that died a long time ago and brought to us by lots of physics and chemistry. So with that, I'd like to end my talk, and thank you for your attention.
Here next. Put this on. Let me.
Oh, yeah.
Oh, no worries. I just wanted to say thank you so much. I thought it was a visually rich presentation. It was amazing. I mean, really well explained, well done. Fantastic. I really enjoyed it. I'm looking forward to seeing it again later. Also, one question I had really quickly was, I loved your animations on it. I'm very visually, much a visual learner. It's amazing what we can get from instruments these days. And so I'm almost flummoxed, like, are those real sometimes? So there's one image you showed of billowing gas and dust.
Yes.
Is that a real image?
No, that's not a real image, but it's
It's
a theoretical model of an AGB outflow.
yes.
But there are some images of AGB stars taken over time, but they're about to be published. But yeah, so there's some very cool stuff going on.
Really brilliant. Really brilliant. Thank you. Any questions from our audience? We do have some online, but I'll take some from the audience first. If you have them, please raise your hand. Hopefully that mic is working.
Do you have any idea of when the first planetary systems were formed?
The first, over the age of the universe. Oh, wow. So the question was whether I have any idea when the first planetary systems have formed, and I don't know the answer off the top of my head, but I assume you have to wait for a while before you have enough dust and gas. But we do know that in the very, very early galaxies, that's what the James Webb Space Telescope is telling us now, there's already a lot of dust, when you wouldn't expect it to be there as well. So I suppose earlier than you might imagine, or at least I might imagine.
I may just build on that. I'll build on that question. I'm trying to get a picture in my mind of the timescale from, let's say, Big Bang till now, and understanding how big the life cycle of a major star is to get some.
Oh, right, yeah. Of course.
10 generations of stars during that period of time.
Oh, there's multiple generations of stars. Exactly how many, that's up for debate, I think. But for example, a massive star, they live fast, they die young, they're only a few million years old. Whereas a star like our sun, that's like a few billion years. So all in all, there's many generations from the Big Bang up until now that have already died and seeded us with all of this carbon and oxygen and everything. So there's many more, but yeah, how long you live as a star depends on your initial mass. So the bigger you are, the shorter your life, generally, from billions to millions.
Yeah. If you look, for example, at a star that's exploding recently, in terms of things, being able to see it within our human lifestyle, lifetime, how long ago did that happen? You look at the nearest one that we've seen explode, how long ago? I'm trying to understand.
Yeah, for that you also need to take into account the distance, right? Because it takes time, well, it takes the light some time to travel to us. So we can only see into the past. But for example, one of the, can I just, like the star that I showed in my beginning slide, he's quite close by. That's like 200 light years away. And the disk one is only 80 light years away. So everything we're seeing now is already 80 years ago. So who knows what it's doing right now, but that's not that long ago. No. Those are quite close by, exactly, compared to, it all depends on your distance. But for the AGB stars, you can study in great detail. They need to be quite close by for you to see all the details as well. So yeah, no, I hope that answers your question.
Fabulous. I think the mic is working now.
Okay.
I do have some questions online. And by the way, Dr. Van de Sande, we have the Sidewalk Astronomy Netherlands joining.
All right.
It looks like they've enjoyed it very much. They just said, too bad it isn't in Dutch.
Oh, I can touch again if they want to.
So, hello. Okay, we have several questions from the Zoom audience. Paul Klein asks from Anglia Ruskin University, if you could magically have a 21st century instrument placed on Voyager 1 or 2, what would that instrument be and why?
It's like it's my PhD 5 all over again, that type of question. So yeah, for the Voyager 1, you would have, well, it was of course built with 1970s technology. So I suppose if you could Well, for the Voyager 1 now you're measuring all of the interaction between the solar system and the interstellar medium. So if you have a nice mass spectrograph or maybe a cool plasma meter, but ideally, well, I'd like to see. So, I mean, you can see some things, but it's not chemically very interesting. I think it would be very interesting to have ALMA, but then on the moon, because then you don't have any atmosphere, which is very useful to us, but it also blocks most of the water lines, for example. So I think that would be a more astrochemically relevant tool, something in space, so we aren't annoyed by the pesky atmosphere blocking lots of lines. But yeah, the Voyager 1 mission, yeah. Maybe an updated spectrometer and an updated spectrograph, that would be nice.
So we have Cass who asks on our Zoom audience, would the rate of molecule formation in the interstellar medium follow a linear increase through time, or would it have changed? I don't know if they're talking about Myra.
So, well, what do you mean by rate of molecule formation? So you've got in a specific cloud, of course, chemistry will happen at a specific time scale, and then it's all a matter of which time scale is longer, which time scale is shorter. If your evolutionary time scale is much, if you evolve much faster, then it doesn't really matter what chemistry is going to happen because, well, we're already at the next stage. But if they went questioning, well, there will be more complex chemistry, the more heavy atoms you will have, of course. The more carbon you have, the more reactions will occur because carbon really likes to react. So perhaps that's another way to answer that question.
Yeah, it's hard to know.
It's hard to know.
Yeah.
Please let us know.
Kang Lee on Zoom as well asks, what do you think is the main source of dust formation in the interstellar and intergalactic medium besides the disintegration of comets?
Interstellar and intergalactic. Well, so for so the main sources of stellar dust, so that is seeded into the ISM. So of course, AGB stars, supernovae also contribute a bit, but then in the ISM, the main rate of formation of dust, because the dust enters the ISM, but then it gets shattered quite a bit because there's like a shock wave breaking all your dust grains apart, but they are reformed as well. So I think it's not necessarily comets being disintegrated, it's more tiny dust grains sticking together and forming larger dust grains again. So you destroy your dust, but then it's also a reformation cycle again from molecules, but those details are also quite tenuous, but not necessarily comets. Maybe interplanetary, yeah, but not intergalactic or interstellar. But perhaps, yeah.
We still have some time, so if you have any questions, just raise your hand. We are looking in the audience. One more from our Zoom audience. Tom asks, you showed a slide of individual molecule detections.
Yes.
It's approximately 6 a year.
Yeah. Oh.
But how do you get enough light to build up enough of a spectrum to identify the molecule?
Well, how do you get enough light? Either you have a big telescope so you can catch more photons, or you just look at it for a very long time. And the beauty of radio astronomy is that you're not constricted to the nighttime because, well, who cares about the sun? So you can just stare at it for like hundreds of hours if you so please. The longer you look, the more photons you collect. And that's also why you've got ALMA, so it's 66 telescopes acting together as one big telescope. So you've got 66 surfaces, and that's a more efficient way of building a kilometer-wide telescope, which falls apart quite rapidly. It's like an engineering issue, then, I think. But yeah, so big surface, stare at it for a long time. Yeah, just stare.
Someone from our YouTube audience, Nicholas, they ask, what instrument, and this may have been what you already answered, but it sounds similar to that question. What instrument has not been sent on any spacecraft that you think we should do in the future, either because the technology was not developed or any other reason?
Right, so it's a lot of pressure on me. I don't do much observations, but like, yeah, I like to see some radio like radio telescopes without being hindered by the atmosphere, because now you can't study water in space because all of the water in our atmosphere absorbs the water frequency. So that would be pretty cool. But yeah, because we now have JWST, so that's already so much information from the infrared and the far infrared as well. But yeah, it would be nice to go into the longer wavelengths as well, I think, like Herschel, the Herschel's telescope, sorry. So many Herschels today, but yeah, a new Herschel perhaps.
So much. Thank you very much.
Thank you.
Hello, I work in the library in the archive. My name's Sian, and you're very welcome to pop into the library to see this month's display, which we put together for International Women's Day. We have 3 sets of lunar observations by 3 women, which have never been displayed in the library before. Well, you'll learn about it if you want to pop up. You're very welcome.
Thank you, everyone. Thank you for coming today.